Let us start our lecture, and the topic is weak convergence of probability measures or convergence in distribution of stochastic processes. I would like to recall you that sequence of random elements with values in a metric space E converges in distribution to a random element xi with values in E if for any f bounded and continuous function from E to R, we have convergence of the expectations. F of xi n is equal to E f of xi. We discussed that if E is Euclidean space, then weak convergence is equivalent to convergence of the characteristic functions, and today we will discuss stochastic processes and just abstract random elements in a metric space. And I would like also to recall you that on this metric space we consider the Borel sigma algebra. Okay. Now I would like to discuss some abstract properties of convergence in distribution and important results. And the first property is the following. Let C in E be a constant, then sequence of random elements converges to this constant in distribution if and only if xi n converges to this constant in probability. Well, we have already known that convergence in probability and almost sure convergence imply these. Okay, see previous lecture. So we need only to prove this implication. And recall what does it mean? So xi n converges to, so we have to prove this. This means that, okay, for simplicity, let me consider E is R, Euclidean space, and I will write just modulus for distance, but all reasoning for arbitrary metric space are the same. You just need to use metric. So this means that probability that xi n minus c greater than or equal to epsilon, that the limit of this is 0 for any positive epsilon, or that limit of probability that xi is close to c is 1. So we need to verify this. Select arbitrary epsilon greater than 0, and let us consider the following function. So this is 1, this is c minus epsilon, c plus epsilon, this continuous and bounded function. And I will denote it by f epsilon of x. So we have convergence in distribution. So for any epsilon greater than 0, limit of expectation of f of epsilon psi n is equal to f epsilon of c, which is 1. On the other hand, the function f epsilon is less than or equal to the indicator function. So f epsilon of x is less than or equal to indicator that x minus c less than epsilon. So the limit of integrals, okay, I don't know if there is a limit, so let me write the lower lim inf of integrals or expectations of indicator that psi n minus c less than epsilon is greater than or equal to limit of expectation of f epsilon of psi n, which is 1. And expectation of the indicator is just the probability of the event. Xn minus c is less than epsilon. So we know that the lower limit of this event is greater than or equal to 1. All these numbers are less than or equal to 1, so the limit of this exists, and this limit is 1. So we have convergence in probability, and the property is verified. The next property is very important result that we will use often, and the result is called continuous mapping theorem. The formulation is the following. Let psi n be a sequence of random elements with values in a metric space E1, and let G be a continuous mapping from metric space E1 to metric space E2. And assume that psi n converges in distribution to a random variable psi as n goes to infinity, then g of psi n, these random variables take values in E2, converge converge in distribution to a random variable, random element with values in E2, g of xi. One small remark, function g is continuous, so it's Borel function. So these are really random elements, so they're measurable. Okay. And the proof is the following. We just need to verify the definition of convergence in distribution. So let f be continuous function on E2, which is bounded. So consider expectation of f of g of xn and write this function, this random element, as composition of f and g applied to xn. The function, the composition of functions f and g is continuous because f is continuous and g is continuous, and this composition is bounded because f is bounded. And we know that xn converges to xi, so this limit is equal to expectation of this composition. So expectation of f of g of xi, and we verified that expectation of function of g of xn converges to expectation of the same function f of g of xi. So the theorem is proved. Uh, also, I would like to formulate without the proof one important result. Again, this result is close to this first one, that convergence to a constant is equivalent to convergence in probability. And the result is the following. Assume that xn converges in distribution to xi as n goes to infinity, and eta n converges in distribution to a constant. So all xi n and eta n are defined on the same probability space. Xi may take values in one metric space. This eta n may take values in another space. And we have convergence of this and this. It appears that sequence of pairs converges in distribution to xi and c. So coordinate-wise convergence implies convergence of pairs. Well, you have to be careful. This theorem is true only if the second coordinate is non-random. Generally, this theorem is not true as proof exercise. So try to prove yourself. If not, you may find the proof you may find the book in Billingsley book convergence of probability measures. Convergence of probability measures. And if xn and eta n, if the limit is not random, then this is not true. And the counterexample is the following. Just take let xi n are non-trivial independent identically distributed random variables, and xi n tilde is a copy of xi n, and assume that xi n tilde that all sequences are independent. Then, of course, xi n converges to xi. Xi n tilde also converges to xi1, but sequence of pairs does not converge to xi1, xi1. This sequence converges to this xi1, xi1 with tilde. So the fact that here the limit is non-random is important. And now I would like to formulate a few important corollaries from this property and the previous one, continuous mapping theorem. Sometimes this corollary is called Slutsky lemma.
Can you go back for 1 second?
Here?
Yes, thanks.
Keys. And we will use this corollary very often. Assume that xn take values in R. So just random variables, and also eta n, and assume that xn converges to xi, eta n converges to C, then xn plus eta n converges to xi plus C, xi n minus eta n converges to xi minus C, and product converges to a product. And if C is not 0, then ratio converges in distribution to xi over C. But here you have to be careful because eta n may take value 0 with positive probability. So you have to consider this random variable in extension of R. So you add plus and minus infinity to the state space. And the proof is simple. So we know from the previous property that psi n at n converges to psi, comma, c in distribution. And now the state space is R2, and plus, minus, and multiplications are continuous maps from R2 to R. So some difference product converge to some difference and product of limits. Well, for ratio, you have to add some necessary reasoning. And the last important, well, not the last, but very important property that we will use very often in our course is called Skorohod's representation theorem. And the result is this. Assume that psi n are random elements with values in E, where E is a separable metric space. Then psi n converges to xi. Well, and xi also is a random element there in distribution, if and only if there is a metric space. Oh, there is a probability space. And random elements xi and tilde xi defined on this probability space such that xi n has the same, for every n, xi n has the same distribution as xi n. Xi with tilde has the same distribution as xi, and xi n tilde converges to xi tilde almost surely as n goes to infinity. We know this direction, that if you have copies of xi n and copies of xi n and xi defined on the same probability space, and if you have convergence in distribution, then you have, if you have almost sure convergence, then you have convergence in distribution. So this implications is simple. Another one is complicated, and the good reference is again Billingsley's book, the second edition. And originally, Skorohod's proved his result with the formulation that you have here convergence in probability, not almost surely. However, later his result was generalized to almost sure convergence, and this result is very useful. Indeed, when we discuss convergence in distribution, we think about random variables, some continuous function f, and we have to check convergence of expectations, and we know this only for continuous functions, and the natural question is, okay, if you have this, for example, and if f is not continuous but discontinuous, say, in one point, can we prove this? Is there like Lebesgue dominated convergence theorem and so on and so forth? But if you have these four copies, then you just fixed omega and work like in mathematical analysis. So then it's like usual convergence. And later on, when you think about convergence in distribution, then recall Skorokhod representation theorem and imagine that you have convergence almost surely, and then work as you have almost sure convergence, and very often it's much easier. The next corollary is generalization of continuous mapping theorem. So let me write a continuous mapping theorem part 2. Assume that E is a separable metric space and a sequence of random variables xi converges with values in E, converges in distribution to xi, and let f be a measurable, let g be measurable map from E to R, and denote by A the set where function g is discontinuous, is x e such that g is discontinuous at x. By the way, this set is measurable. And the reference is again Billingsley's book. Suppose that probability that psi n, oh, excuse me, not psi n, psi in A with probability 0. So psi take values in the set where G is continuous. Then G of psi n converges in distribution to G of psi. By the way, if you don't want to discuss measurability of this set, you may you can transform this theorem as follows. Assume that A is a measurable set such that you have this, and G is continuous on E minus A, and if you have convergence in distribution, then you have this. Okay, and the proof of this theorem is a simple corollary of Skorokhod representation theorem. Indeed, let psi n be copies of psi n and psi n tilde, and psi tilde is a copy of psi, and they assume that they are defined on the same probability space and that you have almost sure convergence. Oops. Psi as n tends to infinity. Then g of psi n tilde converges to g of psi with tilde almost surely. Indeed, if omega is such that psi with tilde doesn't belong to A, then psi tilde of omega tilde is a point of continuity of G. And we know that for almost, okay, we work on the set of probability one that we have this. And then G of psi and tilde converges here for this particular omega because G is continuous at this point. And now let f be a bounded and continuous function on E. Then we have convergence of expectations. By the Lebesgue dominated convergence theorem. Indeed, these random variables are bounded because f is bounded. We have almost sure convergence of f of g of xn to this random variable because we have this and f is continuous. So everything is proved okay. And this expectation is equal to expectation of f of g of psi n, and this is expectation of f of g of psi. So we just verified the definition of convergence in distribution. And if we return back, then we see that the last part of this Slutsky lemma is also a simple corollary of Skorokhod representation theorem. If constant c is not 0. Well, and it's clear that this result can be easily generalized for the more complicated cases. And the next result, which is very close to Slutsky lemma, and this is exercise for you, is the following. Let psi n and eta n be random elements with values in E, where again E is a separable metric space. And assume that in E, so E, okay, so E and metric row. And assume that the distance between psi n and eta n converges to 0 as in probability as n tends to infinity, then sequence psi n is convergent if and only if sequence eta n is convergent. If and only if eta n is convergent. Moreover, their limits coincide. If the limits exist, then they are equal. Well, if E is linear, if E is, say, Banach space, then you can write here eta n is psi n plus eta n minus psi n, and then you say that this converges to 0, and then you may prove arguments of Slutsky lemma. Well, in case of general metric space, there is no difference, so you have to work a little bit.
Excuse me, when we
Yes.
say convergent, it's convergent in distribution, you mean?
Yes, convergent is in distribution. Thanks. In distribution. In distribution. Yes, sure. In distribution. By the way, if we say converges in probability, then this theorem is also true, but the proof is much easier. Well, and now let us continue. And well, my few remarks. Just take a look at Billingsley book. I strongly recommend, and there are important results. For example, Prokhorov's theorem. That give necessary or sometimes necessary and sufficient conditions of weak relative compactness that say that a sequence psi n is weakly relative compact. This means that there are subsequences that converge in distribution. Or, for example, Portmanteau theorem. That is related. So there are 4 or 5 equivalent definitions of weak convergence, and so there is a relation between, say, weak convergence and convergence, say, upper limits or lower limits of probabilities that psi n in A, where A is a certain type of sets, for example, open or close or some other. So just read this theorem and write it in your notes. And now let's consider examples. And my aim is to obtain a Brownian motion as a limit of random walks, of scalings of random walks. So we consider a sequence of ID random variables, B independent identically distributed random variables, mean 0, and variance K1, and consider a random walk as psi of n, which is equal to psi 1 plus psi n. Let me make a picture. Well, as psi of 0 is 0. So we start from 0, then the first increment is psi 1, psi 2, psi 3. So this distance is psi 1, this distance is psi 2, this distance is psi 3. For example, this is psi 4. And we extend S for all t by linearity. So this is time. So S psi of t is equal to if t in n plus 1, then it equals S psi of n plus t minus n S psi n plus 1 minus S psi of n. So it's linear on this interval. If t is n, then result is Sn. If t is n plus 1, then result is S psi n plus 1. We know that the natural scaling of time and space is n and square root of n, and I would like to recall you the central limit theorem that S psi of n divided by square root of n converges in distribution to standard normal variable. And now we consider this random walk, and then we shrink time. So we speed up time n times, and we make scaling for the space square root of n times. And let us consider the sequence of processes xn of t that are equal to S psi n t divided by square root of n. So we clear here n times, here square root of n. Well, so we transform our process. So, and in the limit, okay, if we extend, we will see very irregular path probably. Okay. The first question is, what is the limit of this? And okay, let me write that as psi of n over square root of n converges to n0, 1. And okay, the first non-rigorous and proof is this. Okay, let us divide here by square root of n multiplied by square root of t multiplied by square root of t. Then we denote this. So say this is n, this is n. We know that you have this limit. Okay, so we have converges in distribution to n0, 1 times square root of t, which is equal to normal distribution, 0 mean, and variance t. Well, there are two important so what is wrong in this proof? At first, we know the central limit theorem if this number is natural number. N times t is not in general. So we have to make some adjustments. Well, okay, so let me write the definition. As xi integer part of nt plus, by the way, this is xi n plus 1 plus xi with index nt plus 1 times t minus n divided by square root of n divided by square root of n. And here I would like to apply the central limit theorem, so I will write here integer part of nt. So we multiply and divide by the same value. And then we have two terms. Well, this term is less than or equal to 1. This term converges to plus infinity. And it can be seen that this term converges to 0 in probability. Now, this term, well, now we may apply the central limit theorem. Integer part of nt is natural number, so we have convergence to n01 to the standard normal distribution. This is a sequence of numbers, of non-random numbers that converges to, over square root of n, that converges to square root of t. Okay, this is non-random variable, so the product converges to a product, and the sequence converges to 0 to non-random variable in probability, so their sum converges to square root of t times n01 plus 0. So we applied Slutsky lemma. So the limit is n0t, and we proved that xn of t converges to a normal distribution with variance t. Okay. Questions? Okay, if no, then let us continue. And now let's consider convergence of multidimensional distributions. So let us start with two-dimensional distribution. Assume that S is less than t, greater than 0, and I wish to find the limit of this. And the first question is, are these random variables dependent or independent?
Dependent.
Yes, that's correct. They're dependent. So let me make the following trick. Ns over square root of n, and consider the difference as xi and s plus s s xi n s over square root of n. Okay, my second question is, and what about these random variables? Are they dependent or independent?
Independent.
No, this is not true. Why? Well,
Sorry. You mean the pair or two things in
no,
text?
my question is this random variable and this random variable. Are they dependent or independent? And I state that they may be dependent. Well, if you consider
Say like a natural number, then
yes, because n of t and n times s are not natural numbers. If nt and ns are natural numbers, then they're independent. But we continue the random walk by linearity for all positive numbers, so they may be dependent. And I want to consider independent random variables because, well, I know vector valued central limit theorem. Well, so let me make some work and I'll find independent random variables. So I consider ns integer part over square root of n plus the difference s xi ns minus s xi integer part of ns divided by square root of n. And this random variable is divided by square root of n converges to 0 in probability. So we had this random variable. We have seen this variable in the previous proof, and let's make the same trick here. So s xi n t integer part minus s xi n s integer part over square root of n, and plus s xi integer part of ns divided by square root of n plus something that converges to 0 in probability. So to investigate the limit of this pair, it's sufficient to consider only convergence of these random variables. And okay, small exercise, apply just the usual central vector valued central limit theorem and prove that the sequence of pairs S xi n s or square root of n plus s xi n s. Okay, and prove that sequence of pairs converge in distribution to the pair xi1, xi2. Oh, no, xi is bad notation. Eta1, eta2, where eta1 and eta2 are independent, and eta1 has the normal distribution with variance S, and eta2 has the normal distribution with zero mean and variance T minus S. And then if you have this, then the limit of this is eta1, eta2 plus eta1. So we return back here. The limit is eta1 plus eta2. And we apply here Slutsky lemma and continuous mapping theorem. We know that pair converges to eta1, eta2. So this and this converges to eta1, comma, eta2 plus eta1 because addition is a continuous function. Well, this random variable is Gaussian. Well, we know that eta1 and eta2 were Gaussian, and the mean is 0. And what is covariance matrix? Variance of eta1 is S. Covariance of eta1 and eta2 is S again, because eta1 and eta2 are independent, so covariance of eta1 and eta2 is 0. And if random variables coincide, then their covariance, mutual covariance, is equal to variance. Similarly, you have S here, and covariance of eta1 plus eta2 and eta1 plus eta2 is variance of the sum. Since the random variables are independent, then variance of sum is equal to sum of variances. So the answer is S plus T minus S, so T. Okay. And similarly to this proof, we can verify that for every T1 Tn, the sequence xi n T1 over square root of n xi n Tm over square root of n converges in distribution to a Gaussian vector, zero mean, so where sigma is the following matrix: minimum of Ti and Tj, where I and j between 1 and m. Well, I didn't assume here that T1 is smaller than T2, smaller than Tm. No. That's why this minimum appears. So this is, okay, the property and the exercise for you, but the reasoning is the same as we did before. And now it's natural to define a Brownian motion as a Gaussian process with the corresponding finite dimensional distribution. Stochastic process B of t is called a standard Brownian motion. Or sometimes we say Wiener process. If at first B is a Gaussian process, expectation of B of t is 0 for all t. And the third condition is that covariance of Bs and Bt is equal to minimum of S and T. Oops. Okay, minimum of S and T. Well, all of these means that if you take any natural number m and any t1, t2, tm non-negative numbers, then finite dimensional distribution of bt1, bt2, btm are Gaussian with zero mean and with this covariance matrix. And actually, we proved here convergence in distribution of finite dimensional distribution. So that scalings of random walk converge. So converge to finite dimensional distributions of a Brownian motion. And we know very good properties of random walk. For example, we know distribution of maximum. And it's natural to ask ourselves, can we find the distribution of maximum of a Brownian motion as a limit of maximums of random walk? And the answer is yes, but additional work is required. Well, let me recall you some properties of a Brownian motion. I hope that you have already heard them, but and most of them are not complicated to prove. Well, the first property is that the Brownian motion exists. That there, what does it mean? This means that there is a collection of random variables indexed by time, by t, and these random variables are defined on a certain probability space such that the finite dimensional distributions satisfy this property. This statement follows from Kolmogorov theorem, on existence of stochastic processes. Okay, and now let us discuss other properties. So assume that we believe that Brownian motion exists. The first property is, well, B of t. Just recall you that it has normal distribution and B of 0 is 0 almost surely. The second property is independence of increments. And when we discuss properties of Brownian motion, it's very natural to expect that you have these because random walks have independence of increments. What does it mean? This means that for every t1 less than t2 less than tm, for every m and all t1, t2, tm non-negative numbers, random variables bt1 and increment bt2 minus bt1, bt3 minus bt2, and so on, btm minus btm minus 1 are independent random variables. Okay, I have a question how to prove this property. Are there any ideas?
By our previous construction in the example.
Yes, yes, you're right. We may really apply our previous construction from the example. This is correct, but if you just use the definition of Brownian motion, you may say the following. It's well known that Gaussian random variables are independent if and only if they are uncorrelated. So Gaussian random variables are independent if and only if they are uncorrelated. So let's find covariance of, say, BTI plus 1 minus BTI and BTJ plus 1 minus BTJ. And if we prove that for all I and j, okay, including 1, so here you may write formally like minus b of 0. If covariance is 0, then you'll have independence of all these vectors. Well, for simplicity, let us assume that Ti is less than Tj, and we use linearity of covariance, and we obtain that covariance of this is equal to covariance of Bti plus 1 and Btj plus 1 minus Bti plus 1 Btj minus covariance of Bti plus 1 Btj minus covariance Bti Btj plus 1 and the last Bti Btj plus covariance Btj and Bt Btj. Oops. And if Ti is less than Tj, then Ti plus 1 is less than Tj plus 1, so covariance is equal to minimum Ti plus 1. And here, if Ti is less than Tj, then Ti plus 1 is less than or equal to Tj, so minus Ti plus 1 again, minus here minimal of ti tj plus 1 is ti, and plus, here is ti, plus ti is 0. Okay, so covariances are 0, so random variables are independent. And the next property of a Brownian motion is Brownian motion has homogeneous increments. This means that for any st non-negative numbers, and for any, say, delta, the increment of bt minus bs has the same distribution, not equal, but has the same distribution as bt plus delta minus bs plus delta. So the length of interval, for example, s is less than t, here is t minus s, and the length of the interval s plus delta t plus delta is again t minus s. Moreover, it can be proved that the distribution of this is normal distribution with expectation 0 and variance t minus s. So I review these statements as an exercise. When the proof is simple, you have to find the distribution of this difference. This random variable is Gaussian, this random variable is Gaussian, expectation, so difference is Gaussian. Well, and we know that the vector is Gaussian vector. Difference is Gaussian. Expectation of this is 0. Expectation of this is 0. So expectation of this is 0. So we know Gaussian, 0. We need only to calculate variance of difference. And then you apply independence of increments, for example, and we know that bt and bs have variances s and t respectively. So that's all. Or you may use you know covariance between bs and bt, so it is not a problem. Well, so b is very nice process, Gaussian, independent increments, continuous increments, and the next important property is continuity of b in t. And the statement is the process b of t has a continuous modification. And this means the following, that there is a process b tilde of t defined on the same probability space such that for every t greater than or equal to 0, probability that b of t is equal to b with tilde of t is 1. And b tilde is a continuous process for all omega. And for all omega, b omega, okay, let me write here, the function b tilde omega t as a function of t is continuous. So you may modify b of t somehow on the set of probability 0 such that you obtain a continuous process. One important remark: this property does not mean that probability for every t you have equality. The definition is this. And as an example, you can think about processes that has this property but do not have this one. Well, the proof is based on Kolmogorov continuity theorem that states that if a process X okay, t greater than or equal to 0 has the following property is such that there exists C alpha beta all positive such that for all S and T expectation of x of t minus x of s to the power alpha is less than or equal to c t minus s to the power 1 plus beta, then x possess a continuous modification. So this is sufficient condition, and we will apply it in our situation. So let's consider expectation of b of t minus b of s to the power alpha. Well, we know that this increment is random variable, normal random variable with variance. Okay, I don't know what is greater t or s, so let me write t minus s. Absolute value of t minus s, absolute value to the power alpha, and we know that the scaling property for the normal variable, so this random variable has the same distribution as n01 to the power alpha times square root of t minus s to the power alpha. So t minus s to the power alpha over 2. Okay, let me denote. I know that Gaussian distribution has all moments of Gaussian random variables are finite. So let me denote that constant by c of alpha. And let me write down like alpha over 2 is 1 plus beta. So I have to find some c, alpha, and beta. And if alpha is greater than 2, then beta is positive. So I need to prove existence of positive beta. So take alpha, for example, 4, then beta is alpha is 4, then beta is 1, and C4 is finite. I just need to know that this constant is finite. Well, but I can calculate this. It's well known that the force moment of Brownian motion is 3. Okay, so Brownian motion has a continuous modification, and now let us return to convergence in distribution. A week ago, I formulated you one result that if you have a process with continuous trajectories, then you can consider this process as a random element in the space that take values in the space of continuous function. So, for example, if xt is a stochastic process, okay, it depends on x and on omega, where t in 0t, omega in omega, and assume that this process is continuous. Now let us consider x as a mapping, as a value. So omega belongs to omega, and this is element of C0t. And the exercise was prove that this map is measurable. So the statement is, if stochastic process has continuous trajectories, then x as a function of omega is a random element with values in the space of continuous function. And we have a Borel sigma algebra here, and so on and so forth. And the last and very important result for today, which is called Donsker theorem, that states that if xn are independent, identically distributed random variables, zero mean, variance, okay, sigma squared, then if you consider scaling of random walks, okay, let me write like here, over square root of n, these are processes that are indexed by t, so they are random elements in C0t. Then sequence of these C0t random elements converge to a standard Brownian motion. As n goes to infinity. We know convergence, okay, in the space C0t, where metric or topology is, so this is Banach space with norm, with supremum norm. F of t, t in 0t. I will not prove this theorem. Again, you may find the proof in, say, Billingsley book. Unfortunately, I do not have enough time to prove this theorem. And next time, next lecture, we will find, for example, the distribution of maximum of a Brownian motion as a simple consequence of properties of random walks, simple random walks, and continuous mapping theorem. And that's all. Okay. Thank you for your attention, and see you next week. Uh,